Hello everyone, welcome to CS 350. This is Karthik Gopalan. Today we will continue with the topic of concurrency, specifically with focus on semaphores, condition variables, and producer-consumer problem. Semaphores are a fundamental primitive that's used for synchronization among concurrent processes. Using semaphores, you can implement various types of synchronization, whether it be event notification between two threads or whether it be locking around critical regions. So we will look at both use cases of semaphores in this lecture. So what exactly is a semaphore? Semaphore, you can think of it as an integer, a special integer. So with the special integer, you can do two operations, up or down. The down operation is roughly equivalent to decrementing an integer, and the up operation is roughly equivalent to incrementing the integer. But instead of just incrementing and decrementing, we also add special meaning and special side effects to these operations. So in the next few slides, we will look at what exactly up and down operations do. The down operation works as follows. If the value of the semaphore is greater than 0, then this down operation would decrement the semaphore by 1. At this point, the down operation would return back to the caller, and the caller can continue executing whatever code follows the down operation. Such a down operation is called a successful down operation. There was a positive semaphore, you were able to decrement it by 1, and the subsequent code after down operation was executed. On the other hand, you may have a situation where the semaphore value is 0. In such case, a down operation will not decrement the semaphore value further. Instead, the semaphore value will remain 0 and the caller would block. Basically, the caller would go from running state to blocked state. The caller will remain blocked until some other process increments the semaphore with an up operation. At this point, the blocked caller would be woken up and the blocked caller will attempt to complete the down operation on which it was blocked. If the blocked caller succeeds in completing the down operation, then it will move back to the ready state and then to running state. Otherwise, it will be blocked again until somebody else calls an up operation. So essentially, in summary, down operation is similar to decrementing the semaphore, except that if the semaphore value is already 0, then the caller blocks until somebody calls an up operation, at which point the down operation is attempted again. Now the up operation is simpler than down. So up operation will always succeed. It will always increment the semaphore by 1. If the original value of the semaphore was 0, then the up operation will also have a side effect. It will wake up any process that was blocked on the down operation, so that the blocked process would then compete to perform a successful down. So if there were more than one processes blocked on the down operation, then all of them would compete to perform the down operation. Only one of them would succeed and the others would go back to being blocked. Okay, so let's take a look at a concrete example to see how these up and down operations work. So here we have an example where we have three chairs. Okay, they represent three resources. Now the value of a semaphore, the initial value of the semaphore, represents the number of instances of the resource that's available. So since there are three chairs, the initial value of the semaphore is set to 3, and all the chairs are initially empty. Okay, gradually people will take over these chairs one by one, and we will see how the value of the semaphore changes as the chairs get taken. So when the first person occupies a chair, he performs a down operation on the semaphore. As a result of the down operation, the value of semaphore goes to 2. It is decremented from 3 to 2. If the next person comes in, there are still 2 free chairs. So the next person takes the next free chair and performs a down semaphore. So before you take the chair, you perform a down semaphore. If down succeeds, you take the chair. So the semaphore value is again decremented to 1. Note that so far the semaphore value is greater than 0. So all the down operations are succeeding. So we have one more free resource. So the next person performs a down operation that succeeds and he takes the chair. Okay, so basically at this point semaphore value is 0, which means that there are no more free resources available. So what happens if the next person comes in? When the next person comes in, he tries to perform a down operation, and since semaphore is 0, he cannot get a chair. So he's blocked. So he has to wait till somebody leaves the chair, which means somebody performs an up operation. At this point, one more person comes in. He also attempts to perform a down operation. He wants a chair, but there are no more chairs. So he is blocked in the down operation. Note that both the red and the blue persons are blocked on down operations. Their down operation isn't complete. Instead, they are in a blocked state. So the only thing that can wake them up is an up operation by one of the persons who is already occupying the chair. So let's say one person leaves the chair, and then he performs an up operation. Up operation increments the semaphore by 1. This is an indication to the blocked callers on down that they should attempt to successfully complete the down operation. So both the red and the blue persons would compete to acquire the chair. So at this point, the blue person acquires the chair and he successfully completes the down operation on the semaphore. The semaphore value goes back to 0. Now, let's say another person leaves the chair and performs an up operation. At this point, semaphore value goes to 1. Then the other person performs an up operation and the semaphore value goes to 2. You may notice that the red person, although he was woken up from the down operation, his down operation isn't yet complete and he did not yet get time on the CPU, so he wasn't able to complete the down operation. In the meantime, the third person performed an up operation. So this is an example of concurrency where you have multiple processes executing independently. So there's no guarantee that just because an up operation incremented the semaphore value to 1, the blocked callers may be executed immediately. In fact, the blocked callers may have to wait quite a while before they can attempt to perform a down operation. It really depends on what the CPU scheduler is doing at that point in time. So we have now 2 free resources, and at this point the blocked caller successfully completes a down operation and gets the chair. All right, and they are still not happy because they had to wait. So so there's a special type of semaphore called mutex. Mutex is basically a binary semaphore whose value switches between 0 and 1. What that means is that initially the initial value of a mutex is 1, and when someone performs a down operation its value goes to 0, and when someone performs an up operation its value goes back to 1. So the mutex can be used as a lock. We talked about critical sections earlier in the lecture. So using a mutex, you can essentially acquire a lock on a shared resource, then execute a critical section, then release the lock using an up operation. The last bullet in the slide shows what the code structure looks like You first perform a down on mutex, then you execute the critical section, then an up on mutex. Again, going back to the chair example, here mutex is initialized to 1, which means there's only one instance of the shared resource, and the act of acquiring the chair is the critical section. So when the first person comes in, the down mutex operation succeeds, the mutex goes to 0, and the resource is taken. When the next person comes in, the down mutex operation blocks. When the first person leaves and performs an up mutex, it means he is releasing the lock on the shared resource, and the mutex goes back to 1. Then the blocked person gets to successfully perform the down operation, and the mutex goes back to 0. So this leads us to a classic problem called producer-consumer problem. Now we know exactly how semaphores work, and we know what locks mean. We know what critical sections mean, right? So we can put all these pieces of information together to understand the producer-consumer problem. The producer-consumer problem is a very fundamental problem in computer science. In any instance of concurrent systems where the concurrent threads or processes need to talk to each other, you would encounter the producer-consumer problem. In its most general form, producer-consumer problem consists of two classes of processes: the producers and consumers. Producers produce something and consumers consume those things. All right. So the way this works is that when producers produce something, they insert it into a common buffer. The buffer has fixed number of slots, and at any point in time it can only hold so many items. So in this case, maybe the buffer has n slots, so the maximum number of items that the buffer can hold is n. So, and on the other side there are consumers who remove an item from the buffer and consume it. So there are two types of synchronization required here. The first is that since there are multiple producers and multiple consumers, they are all trying to manipulate the shared buffer. So the shared buffer is a contented resource. Remember that insertion and removal of items into a shared data structure requires a lock. For example, if it's a circular linked list, then in order to manipulate the linked list, you need to acquire a lock on the linked list. Or if it's a circular array, you need to acquire a lock on the array. So first of all, any producer or consumer, before he inserts or removes an item, he has to acquire a lock on the shared buffer. The second synchronization primitive is a new form of synchronization primitive that we haven't yet encountered. So note that if all the buffer entries are full, let's say the entire buffer has n entries, then producers cannot insert any more items. A producer who wants to insert an item into the buffer will have to wait till there is an empty slot in the buffer. Similarly, if all the slots in the buffer are empty, then a consumer who wants to consume an item has to wait. So there are three synchronization requirements here. One is that when all the buffers are full, then we need to inform the producers whenever there is an empty slot to be filled. Similarly, when all the slots are empty, then we need to inform any waiting consumers when there is at least one item to be consumed. And thirdly, all the manipulations of the shared buffer should be protected by a lock. So here's a pseudocode for a producer-consumer problem. Here we have two routines, producer and consumer. The structure of the two routines is very similar, but except that the operations are in slightly complementary order. So how do we solve the producer consumer problem? We have two types of semaphores. One is a mutex, and there are two general semaphores. So the general semaphores are also known as counting semaphores because the semaphore counts the number of instances of a resource. So we have a mutex which guards the shared buffer. It can be either 0 or 1. So the mutex is initialized to 1. N is the number of slots in the shared buffer. So initially the number of empty slots is n. So we have a semaphore that counts the number of empty slots, which is n. And then there is a third semaphore, full, which is initialized to 0, indicating that initially there are 0 full items in the buffer. So as the buffer gets filled, empty will be decremented and full will be incremented. So if you look at the code for the producer executes in an infinite loop. Initially he produces an item, and then before inserting the item into the buffer, he performs a down on empty, meaning that he wants to claim one empty slot in the buffer by performing a down operation. Next, he performs a down on mutex, which means that he wants to acquire the lock on the shared buffer so that nobody else modifies the shared buffer. At this point, he has control of the shared buffer, and then he can insert the item into the buffer using the insert item routine. Once the item has been inserted, then he releases the lock on the shared buffer using an up operation on the mutex, and then he indicates to the consumer that there is at least one item to be consumed from the shared buffer. So for this, the producer performs an up on the full semaphore. So if you notice this sequence for the producer, the initial down empty operation can block if empty is 0. What that means is that if all the slots in the buffer are full, then empty will be equal to 0 and the producer will have to wait on the down empty step. Similarly, when the producer performs an up operation on full, and let's say the full value of full was 0, then the value of full goes to 1, and at that point all the consumers who are blocked on the down would be woken up and they would compete for the down operation. So the structure of the consumer routine is very similar, except that the use of full and empty is complementary. So the consumers also execute in a while loop, and each consumer would first perform a down on the full semaphore, which means that it makes sure that there is at least one full item, and it claims an item by performing a down on full. Then it claims a lock on the shared buffer by performing a down on mutex. Then the consumer removes an item from the shared buffer using remove item routine. And then it performs an up on the mutex to release the lock on the shared buffer. And then it performs an up on the empty semaphore to indicate to these producers that there is at least one empty slot in the shared buffer since an item has been consumed. So, and finally, the consumer consumes the item. Note that we defer consuming the item till the consumer is out of the critical region. So critical region is the part where we manipulate the shared buffer, and we don't want to increase the length of the critical region more than what is necessary. So as a result, consuming the item or producing the item in the case of producer, these are not really parts of the critical region, so hence they are outside the lock. So again, you're applying the same logic to the consumer. If full was 0, then the initial down operation on full would block the consumer. The consumer would have to wait till a producer performs an up on full. Similarly, if empty was 0 and the consumer consumes an item, then empty will go from 0 to 1, and that would result in all the producers being informed that there is at least one empty slot in the shared buffer. So semaphores have a number of interfaces that are provided in the C library, and some of those interfaces are shown here. I would encourage you to look up the man pages and online tutorials to see how to use these semaphores. But again, these semaphores are for use between processes. So so if you have any questions about how the semaphores work, feel free to ask me or the instructor. We're going to skip the specific programming details from the lecture. There's also an older interface for using semaphores, the System 5 interface. Again, it has some problems with atomicity of the semaphore operations, but the interface is still available. So some of the tutorials may refer to the old interface, just in case you encounter some of them. So next we will look at another form of synchronization called monitors and condition variables. So monitor is a collection of functions that operate on a shared resource. The purpose of a monitor is to control access to the shared resource by concurrent processes. So the way monitors work is that, let's say there are a bunch of functions that are part of the monitor. In this example, there are two functions, function 1 and function 2. So the semantics of the use of monitor is that only one process could be executing a function in the monitor at any point in time. You cannot have two different processes in the monitor at the same time. What this means is that there is a giant lock that guards all the functions together. So before executing a function, a process has to acquire the lock on the monitor, and once the process exits the function, it will release the lock on the monitor, and at that point some other process can enter the monitor. So essentially, by associating a lock with a set of routines, or basically several pieces of code, we are controlling access to the shared resource on which these routines operate. So in this example, maybe in the integer I is a shared resource that function 1 and function 2 want to operate. So earlier we had discussed a general rule of thumb that you should associate locks with shared resources rather than with code. But monitor is an older form of synchronization mechanism where it is more convenient to associate a lock with code rather than the shared resource itself. In fact, we are associating a giant lock with all the routines that access a specific shared resource. This reduces concurrency to some extent compared to using semaphores, but it also simplifies the code that for concurrent programs. So in many cases, using a monitor is actually simpler than using a semaphore, at least in terms of programming effort. There is a basic problem that comes in monitors. Let's say a process is executing in function 1 and it has to block for some time. Now blocking is a problem because when you're executing inside a monitor, you hold the lock on the entire monitor, which means that no other concurrent process can enter the monitor. So if the process wants to block on an event that will be triggered by the execution of another function in the monitor, then the blocking process has to release the lock. So this is done in an atomic fashion. So when, let's say, process 1 executes function 1 and it needs to block, it will call a special function called wait. When the process calls wait, it releases the lock on the monitor and it blocks for the lock to become available again. At this point, other processes can enter the monitor, and once, let's say, process 2 enters the monitor and executes function 2, it satisfies some condition that would wake up the process 1 that was originally blocked. So at this point, the process 2 would use another special function called signal to indicate that a specific blocking condition has been satisfied. So wait and signal go hand in hand. One process will block waiting for a condition and another process would signal that condition. So signal is non-blocking. It simply indicates that a condition has been satisfied and the process continues until it exits the monitor. Wait, on the other hand, would block the process, release the lock, and once this condition has been signaled, before returning from wait, the process would have to compete again to reacquire the lock on the monitor. So although wait looks like a simple function, internally its behavior is a bit complicated. Initially you release the lock, then you block, and then the process has to compete again to reacquire the monitor once the condition is satisfied. So let's see how this works with a simple example of producer-consumer problem. So we have the same producer-consumer problem as before. We had seen earlier how to solve it with semaphores. Here we will see how to solve the producer-consumer problem using monitors and condition variables. So we have two procedures, producer and consumer. The producer procedure is executed by producers and consumer procedure is executed by consumers. So the producer is in an infinite loop. It produces an item and calls an insert routine. And the consumer is also in an infinite loop. It removes an item from the shared buffer and consumes the item. So the insert and remove operations are part of a monitor called producer consumer. Now in this monitor we have two condition variables, full and empty, and there is a count which keeps track of how many items are there in the shared buffer. In the insert routine, you first check if that count is equal to n, which means if the buffer is already full. At that point, the producer has to wait, so it calls the wait operation on the condition variable full. So essentially the producer has to wait till there's at least one free slot. Once there is a free slot, the producer would be woken up, it would reacquire the lock on the monitor, and at that point it would insert the item into the shared buffer and increment the count by 1. If count is equal to 1 when after incrementing the count, then it would signal to all the consumers that there is at least one full slot in the shared buffer using signal on empty. Similarly, the remove operation works by as follows. This is called by the consumers. First, the consumers check if the count is 0. If so, then they have to wait on the empty condition variable and they would block till there is at least one item to be consumed. Once they succeed on the wait operation, then they can remove an item. Then the consumer decrements the count. If the count goes from n to n minus 1, then it's an indication that the shared buffer has one empty slot. So they would signal any blocked producers using a signal on the full condition variable. So, these two routines, insert and remove, are part of one giant monitor. Then there's one giant lock on the whole monitor. What this means is that there can be only one producer or one consumer performing an insert or remove operation at a time. So although structurally, functionally, it has the same effect as the semaphore based solution, but a key difference is that the level of concurrency that you will get using monitors is lower than you would get with semaphores. I would encourage you to examine carefully how the level of concurrency is different between a monitor based solution versus a semaphore based solution. Finally, we're going to look at how locking is performed. So far we have looked at locking and unlocking as single operations, but the actual implementation of locking by itself is very important. So lock and unlock need to be atomic operations, meaning that you should not be able to split them into multiple steps that could be preempted in some manner by the CPU scheduler. Usually there are some instructions that are provided by the hardware to enable atomic locking and unlocking. So one such instruction is the TSL instruction, or the test and set lock instruction. The general format of the TSL instruction, it varies from architecture to architecture, but the behavior in the most generic form is as follows. The instruction would take two arguments, register and lock. Register is a CPU register and lock is a location in the main memory. If lock has a value of 0, then the shared resource is taken. If lock has a value of 1, then the shared resource is free. So TSL works by doing two operations atomically, meaning that the two operations are done as one step without letting the CPU scheduler preempt the process between these two steps. So the first step is to copy the old value of lock into the register, and the second step is to set the value of the lock to 1. So as a result of the TSL instruction, you are guaranteed that the end result is that the value of the lock is 1, but then the old value of the lock is copied into the register. So after executing a TSL instruction, a process can examine the register to see whether the lock was already taken or not. So if the register value is 0 after TSL instruction, it means that the value of the lock changed from 0 to 1. It means that the calling process successfully acquired the lock. On the other hand, if the value of register was 1, it means that the lock had already been taken by some other process. So the calling process was not successful in acquiring the lock. So using this, let's see how you can implement a mutex, or a binary semaphore. So here we have the mutex lock routine, where you first execute the TSL instruction on the mutex with a temporary register, and then you compare the register value to the number 0. If the old value of the register was 0, then you jump out of the lock routine. It means that acquiring the lock was successful. If the value was not 0, which means it was 1, then you call thread yield. The caller would call thread yield. What this means is that the caller gives up the CPU temporarily so that somebody else can unlock the lock, and then it goes back to the beginning Once the caller gets back the CPU, then it would jump back to the beginning and try to acquire the lock again. So, that's a simple binary semaphore or a mutex implemented using a TSL instruction. The unlock operation is really simple. Since the mutex is a location in the main memory, all you need to do is atomically write the value 0 into the mutex, and this would free up the lock. So there's also a C syntax for the same thing. Essentially, you have a while loop where you call TSL, and as long as uh, TSL returns true, which means that the lock was taken, you keep executing. Once TSL returns false, then you exit from the while loop, and the lock acquisition is successful. Finally, I will just end with one more instruction called compare and set instruction. So this is a more generic and more powerful form of atomic instruction that can be used to implement um, uh, uh, more expressive synchronization mechanisms. So Intel's version of compare exchange is called CMP XCHG. The way this works is that you are given a memory location and you compare the memory location against a given value. If the given value equals the memory location, then you assign a new value to the memory location, otherwise you return the old value. So compare exchange is slightly complicated. It takes two explicit arguments, new val and a memory location. In fact, the memory location would also be a register, but we will skip that detail for now. So in addition to these two explicit operands, there are two implicit operands, the EAX register and the eflags.zf bit. So the EAX register contains the given value and which is compared against the memory location, and it also returns the final value of the memory location. The ZF flag indicates whether the exchange was successful or not. So the way compare exchange works is that you compare the contents of the EAX register, that is the given value, against the memory location. If the comparison succeeds, then you set the ZF flag to 1 and set the memory location to the new value, which is the second operand, the first operand. If the EAX to memory comparison was not successful, then you set the ZF flag to 0 and set the EAX register to the contents of the memory location. So by examining the ZF flag, you can figure out what happened to the compare exchange operation. So note that all of these steps are executed atomically. Although it looks like there are multiple steps, but all these steps are executed atomically without any preemption by the CPU scheduler.